Hi, I'm Liew, and I'm going to present about sound and partially complete static analysis of data races in GPUs. This is joint work with Tiago, Cogumbreiro, and Julien, Lange. So a bit of background, GPU graphics processing units, GPUs, are devices that specialize in highly parallel computations. They're used in many sectors such as 3D graphics, machine learning, systems biology. So how they work is they run a large number of concurrent threads on multiple layers of shared memory. So failing to reason about correctness when writing GPU programs can lead to concurrency errors, such as data races. So what is a data race? It happens when two or more threads access the same memory location, and at least one of those threads are writing to that location. So data races cause undesired non-deterministic behavior, memory corruption, and program crashes. So there are two main ways to handle data races. One is we create a data race freedom verifier, which verifies the absence of data races in the program. So we check that no data race exists in all possible execution paths. The other way is we create a data race finder, which detects the presence of a data race and finds and reports the program execution that leads to that race. So the main property of a data race freedom verifier is to check data race freedom. So we can define soundness as if the tool proves a data race freedom, then the program must also be data race free. So no false negatives. And completeness is the opposite, where if the program is DRF, then the tool must be able to prove DRF. So no false positives. Data race finders are the opposite of that. So soundness in a data race finder is if the tool proves a data race, then the program must also have a data race, no false positives. So completeness is when the program has a data race, then the tool must be able to prove that data race. So we see that it's like the flip side of each other. So for this presentation, we're going to stick to the data race freedom verifier definition of soundness and completeness. So completeness just means no false positives, and soundness, no false negatives. So most DRF verifiers are sound. They aim to be sound. So we can trust when the tool reports DRF. But however, when the tool reports data races, they can be impossible data races in the program. So this leads to false alarms, and we consider that incomplete. Data race finders aim to be complete, so we can trust a data race finder's reports of data races. But when a data race finder reports a DRF, they can miss actual data races, so it's considered that false negatives, and they're normally unsound. So most DRF tools are usually static checkers. They check without running the program, which are approximations. Examples of such tools are File, GPU Verify, and Pug. Data race finders are usually dynamic, usually under approximations of the program. Examples of these are HiRace, HACCRG, and Scored. So you want to build upon our previous two File to keep the sound data race free reports while tackling the incomplete data race reports to be partially complete. So in this paper, we present File AA, which is a static data race finder for GPU programs, while also maintaining the capabilities as a sound data race free verifier. So we characterize a class of programs where our analysis only produces true alarms. We find that to be around 60% of programs. We formally established the root causes of false alarms in File AA, so to determine the sources of approximation. So the structure of this talk will be in two parts. Firstly, the empirical results of File AA. We asked two questions. Can File AA verify bug fixes in open source projects? And does File AA have fewer false alarms than the state-of-the-art? Second part is the theoretical results, mechanized in about 16,000 lines of code, code. I'm going to present about control flow independence and data independence, and then establish our True Positive Theorem. So the first question, can file AA verify bug fixes in open source projects? We found 6 bug fixing commits from GitHub, from OpenMM, and Megatron LM. So we want to run the state-of-the-art on the buggy version of the commits and then the fixed DRF version of the commits. So here we have 3 tools, file AA, file, and GPU verify. Firstly, we run on the RACI buggy version. So we preferably want a high number of true data races or potential data race reports and no data race free and crashes. And we find that file AA has the highest true data races and potential data race reports, so all of them are reported as data race. We see that file crashes on most of them, and GPU verify even reports 2 as DRF, so that's an unsound report. And we noticed that only file AA is able to report true data race reports out of these tools. So for this fixed data race free version, preferably we want DRF reports and no data races and crashes. So we find that file A reports the highest number of DRF and does not crash on any of them. So we can able to confirm 5 out of 6 programs. So for the second question, does file A have fewer false alarms than state-of-the-art? So to do this, we reproduce an experiment by Bardsley in CAF14, where we have 226 reportedly DRF programs from NVIDIA and Microsoft and some simulation benchmarks. So again, we run the 3 tools on this data set. So preferably we want, since this is a supposedly DRF data set, we preferably want a high number of DRF reports. And we find that file AA is the highest among the 3 at 93%. Also, we have the lowest amount of potential data race reports at 1.8. So about approximately 1.9 times fewer potential alarms than the other tools. The second important thing is that we were able to find 10 undocumented RACI programs, so true data race reports in this well-studied data set. And 6 of these programs are both missed by file and GPU verify. So let's formalize the sources of false alarms. Here's the pipeline of our tool. So we take a CUDA program, inference that into a memory access protocol, and then finally quantify into a SMT formula. So a memory access protocol is a type that codifies the behaviors of threads over shared memory. For scalability, memory access protocols abstracts away what is written to and read from arrays. So the contents of arrays are lost during that inference process from CUDA to maps. And it is that inference that causes the approximation in our analysis, leading to false alarms. So here we have an example of a GPU program. It takes an input array A, reads from A, and then writes to A. We classify this as a control flow independent, data independent protocol. So that means that the inference process from CUDA to maps is exact, it has no approximations, and that the contents of A is independent to our analysis. So here we have a variation of that program. So the write now is in the conditional, and that conditional is dependent upon what is being read from A, the contents of A. So we call this a control flow dependent protocol. So this write access may or may not execute depending on what is in A. So the reachability of this is inexact. So thirdly, we have another variation. So the write is now writing to what is being read from A in that variable J. We call this a data-dependent protocol. So the reachability here is exact, but the exact index location in which we're writing to is inexact, and it's dependent on A. So how common are CIDA programs? So we had a data set of 2,700 programs, real-world programs. We retrieved this from GitHub. We find that around 59% of real-world programs are CIDI, so our analysis is exact for these programs. So we have how does control flow independence work? We have a type judgment that states that the control flow of the memory access protocol is unaffected by symbolic variables. And also for data independence, which states that the indexing expression of protocols is unaffected by the non-deterministic variable declarations. And we established some theorems for action set correspondence. So the first theorem basically is our soundness property, which states that any access we find in the program is also in the memory access protocol. Second one is that if the memory access protocol is control flow independent, then we know that all the accesses are reachable in the program, but the indexes may be imprecise. And the third one is that if the memory access protocol is data independent, then the accesses are precise. The index are precise, but it may be unreachable in the actual CUDA program. And finally, if the maps is both control flow and data independent, then all the accesses in maps are also in the CUDA program. So now we can finally establish our true positives theorem, which states that if the maps is control flow and data independent, then any data race we find in maps must also be in the CUDA program. So we've now characterized the class of programs, the CIDI programs, where our analysis can only produce true data race alarms. So to conclude, I presented an approximation analysis, which is a static technique to detect true data race in GPU programs. It uses 2 dimensions of preciseness, CIDI. We established a true positives theorem, which identifies the class of programs where our analysis reports only true alarms. We implemented these techniques into PhiLAA, which is the first sound static DRF verifier that's also partially complete as a data race finder. So our evaluation on PhiLAA shows that it emits 1.9 times fewer potential alarms, and we found 10 undocumented data races in a well-studied DRF dataset. We confirmed 5 bug fixing commits in real-world open source projects, and our analysis is exact on 59% of kernels. Yeah, thank you.
Any questions from the audience? Maybe let me just ask some simple questions. So you say like the approach is partially complete. So in what sense is that partially complete? Like is that complete for the specific class of programs?
Yeah.
Or?
Yeah, so for specific CIDI programs, we know for sure that all reports are true. But if they are not within that class of programs, we can't be trustworthy on the reports. But we do know the sources of where the approximation may come from.
Okay, so maybe I ask one more question. So do you consider like to design a domain-specific language based on your observation? So as a programmer, if you use your DSL, then it's guaranteed to be CIDI, and so you can directly use the analysis to find true positives.
Yeah, if the program is CIDI, then yeah, we can confirm the true positives.
So if like you can design a domain-specific language, it's also doable?
Yeah, we haven't looked into that, but yeah.
And any more questions? Yeah, thanks.
Thanks for the great talk. May I ask what makes the GPU program so special? Can similar techniques be applied to such as like CPU programs in general?
So GPU programs they run parallelly, so we have to reason about how it executes in parallel. So that's a bit that's what makes it different from CPUs. There are also different levels of memories. So that's what makes it special, I guess.
Thanks.
Yeah.
Any more questions? Okay, so thanks again for the wonderful talk.